In this skill, we're again mixing together an acid and a base. This time, we're mixing together a weak acid and a weak base. We're mixing them together so that they react completely with each other, and our goal is to figure out what our pH will be at equilibrium. In this question, we're mixing together some ammonia solution with some hydrofluoric acid solution. That's a weak base and a weak acid. So they react completely together at 25 degrees C. React completely means we're not going to have an excess of one of them. So the reaction is going to happen completely. We're going to have all the NH3 and all the HF react together to form NH4F. We can see what's happening in terms of our net ionic equation. Everything from the molecular equation is also shown in the net ionic equation, except the salt that we produce is shown as its separate ions. We've also been provided with the dissociation constants, Ka or Kb, for each species provided in the table. So let's just go ahead and figure out what's our acid and our base, and what's our conjugate base and conjugate acid. So NH3 ammonia, we know that's a base. And we can see here, it gains an H plus ion to become NH4 plus. That means NH4 plus is the conjugate acid of ammonia. Then we have HF, which we know is a weak acid. That's going to lose an H to become F minus. So that must be the conjugate base. That's why we have Kb for NH3, which is a base, and Kb for F minus, which is a conjugate base. And we have Ka for HF, which is our acid, and Ka for ammonium, which is our conjugate acid. Okay, so to figure out what our pH is going to be at equilibrium, we need to think about which is stronger of our acids and bases here. So our first question asks, which is the strongest acid? So we're comparing HF with NH4 plus. HF has a Ka of 6.60 times 10 to the power of negative 4. NH4 plus has a Ka of 5.80 times 10 to the power of negative 10. This number for HF is a lot bigger than this number for NH4 plus. So since it has a bigger Ka for HF, that means HF is a much stronger acid. So which is the strongest acid? It's HF. What about for the bases? We have NH3, which has a Kb of 1.72 times 10 to the power of negative 5. And we have F minus, which has a Kb of 1.52 times 10 to the power of negative 11. So the Kb for NH3 is much bigger than the Kb for F minus. So that means that NH3 is the strongest base here. We're then asked which side of the reaction features the stronger acid and base. So our strongest acid was HF. Our strongest base was NH3. So that's going to be the reactant side of our equation. The reactants have the stronger acid and stronger base. So NH3 and HF being the stronger acid and base means that the forwards reaction is happening at a greater rate than the backwards reaction. That means that our products are going to be favored at equilibrium because we have that stronger acid and base in our reactants. We're then asked what the equilibrium constant will be. If our products are favored at equilibrium, that tells us our equilibrium constant K is greater than 1. If neither our products nor reactants are favored, that means our equilibrium constant K is just equal to 1. If our reactants are favored at equilibrium, then K will be less than 1. So far we've figured out that at equilibrium we will have more of our products than we will of our reactants. So our last step is figuring out, of the species that are favored at equilibrium, which has the greater dissociation constant, Ka or Kb. So I'm now comparing my conjugate acid and conjugate base dissociation constants. I can see that Ka for ammonium is 5.80 times 10 to the power of negative 10. Kb for fluoride ion is 1.52 times 10 to the power of negative 11. So the Ka of NH4 plus is greater than the Kb of F minus. So which has the greater dissociation constant? It's NH4 plus. Since NH4 plus is an acid, that means that our solution is going to be slightly acidic in the end, because of the species that are favored at equilibrium, the acid is stronger than the base. So we're going to have a acidic solution in the end. So to summarize in these questions where we have equimolar reactions of a weak acid and a weak base, we're going to be figuring out which side of our reaction is favored at equilibrium. The side that has the strongest acid and strongest base is not going to be favored at equilibrium. It's the other side that gets favored at equilibrium. Then, of that side that's favored at equilibrium, which one has a greater dissociation constant? Is it the acid or the base? If the acid has a stronger dissociation constant, the solution is going to be acidic in the end. If the base has a greater dissociation constant, the solution is going to be basic in the end.